So I guess first of all, a bit about my own group, because I'm a relatively young faculty, and also my group is relatively young as well. So my group's name is SGuard, or Autonomous and Smart Systems Guard. So we have a grand vision of trying to secure those emerging technologies that makes our physical world more intelligent and more autonomous. So our core expertise is in security, more specifically in the software and AI security. So we used to do research a lot in the cyberspace, for example, for example, web or network protocols or software in desktop, smartphone. And now as the computer technology gets more and more into the physical world, so we also do more research in the cyber physical systems, right? For example, the self-driving car systems that we'll be talking about today. So in my research, one unique thing is that besides like writing papers, we also try to make practical impacts. So for example, we'll make some like attack video demos for the attacks or vulnerabilities we discovered. And also we will report the discovered vulnerabilities to, for example, the vulnerability management agencies like CVE, like US CERT, like Android, and also the developers like Android, Linux, Apple, Comcast, Microsoft. And now as we perform research more and more into the autonomous driving space, so we also report to the companies in those areas as well. And of course, for the US DOT for the smart transportation infrastructure related problems. So for today, I'll be talking about our recent focus. This is kind of a direction that we newly started since I joined UCI. Essentially, we call this so-called autonomy software security in the smart transportation. So more specifically, in recent years, there are two potentially very prominent technology advances in the smart transportation field. One is autonomous driving, AD, of course, like making cars drive by themselves. And second one is the connected vehicle, or CV, that tries to use networking technology to wirelessly connect different elements and users, like the vehicles, buses, traffic lights, and to share information. So there are lots of the companies behind this. I guess the over 40 or 50 companies are trying to do this, and also with the government. And then also at UCI, so we have a self-driving taxi here, and then this is the car operated by Pony.ai, and then this is the in-vehicle view of this self-driving car, which we're shooting for this level 4 self-driving taxi service. So to study the security of this emerging technology, so the unique end of my group is essentially looking at the autonomy software side. Like for example, basically the brand that behind this smart systems that tries to make the driving or transportation operations to be more autonomous and smarter, right? So why looking at this autonomy software of this kind of systems in terms of studying security? Well, the first is definitely importance, right? Because this kind of software is in charge of those core decision-making process for the physical control, for example, driving, which means that errors in this kind of software can directly cause safety hazards. For example, those fatal crashes by like Uber or like Tesla, and especially for Tesla, there are more and more being observed in recent years, especially I guess this year and last year. And second is research value, right? So we are researchers, we care about the research merits. So first of all, there are many new research challenges upon the existing work on AA and CPS, like security. There are lots of research in this, especially in this workshop. So one thing is about the problem formulation, right? Because in this case, we are looking at this production or industry in AD systems or CV systems in the public transportation domain. So there are new domain-specific attack vectors, defense opportunities, and also defense or attack goals or requirements that can be formulated in a new way. So there are some research value there. For example, what kind of attack vectors can be practically deployed in the driving environment, right? Instead of like assuming that you can so one is hacking like into a car and add some pixel level like changes of images. So what are the deployable ones, right? More the practical ones. And second is about methodology, right? So this is also something we care about when talking about research value. So one thing is about the semantic gaps between the system level and a component level security properties. Like, what do I mean by that, right? So first is the gap between the perturbations at a semantic or domain-specific input space level. For example, those road obstacles or road surface appearance or positions or trajectories. So how to map perturbations at that level to those at the component level. For example, the AI model input space, which have been studied in the AI security space, but there's a gap in terms of the input space. And second is from the component level errors, for example, the frame level misclassification to the CPS system level effects, for example, like crashes, right? So that's something we care about in this problem space. So there are some challenges here. So for example, first thing is about there are some error tolerant designs in the later CPS system steps or components, for example, sensor fusion or the tracking actually. And also another one is about a closed loop or feedback control, which is the fundamental component in autonomous CPS because it needs to drive by itself. And in this case, vehicles can actually self-correct, right? If the component level errors is not handled carefully and controlled carefully by the attacker. And besides these semantic gaps that we need to fill, and then there are also general challenges in the methodology, like ineffectiveness. For example, there's a user requirement for differentiability for the security analysis to be effective, and also scalability, right? So in the CPS area, we talk a lot about formal methods and verification, falsification, and then how about the scalability that is due, and also robustness. And on the attack side, there's stealthiness, realizability, transferability. And of course, for the defense side, we also care about overhead, deployability, usability, so on and so forth. So these are more general, but still many times because of the semantic gap and domain-specific attack vectors, we need to handle this as well. And second is that there's a necessity and benefits from the defense perspective. So first of all, there do have some autonomy software specific security vulnerabilities besides the sensor or actuation attacks, right? For example. One example is about corner cases in the AI model. So we know that, for example, stickers on the stop signs can fool the DN, the model. So in this case, this is specific to the DN model itself, not something on the sensor side or the actuator side, right? So this is specific to the autonomy software. So in this case, it is more fundamental and also general if we solve it at the root, right? For example, the AI model hardening. And second, research in autonomy software security side is actually complementary to those attacks and defenses at other layers, right? For example, like sensing and actuation. For example, like attacks at the autonomy software side can escalate the effects or damages of sensor or analog attacks, and also can mitigate them, right? For example, like you can use software only techniques to detect some unique patterns of the sensor input. And last but not least, so the software-only solutions usually has a very big benefit that has very low cost and also high deployability, right? For example, you can solve a problem with only a over-the-air update instead of like hardware change, right? In terms of the CPS. So I will be talking, I'll be giving some examples about these benefits and challenges while I'm talking about concrete research in my group later. So let's jump to the meat. So essentially, first of all, I'll be talking about the AD systems. So before I talk about CV, so there are depends on time. If I don't have time, I'll be probably just quickly skimming through the CV side, but then focus on AD side because autonomous driving is gaining more and more momentum, much more momentum in the recent years, and even more than the CV in general. So yeah, I'll be focused on the AD side more. So some preliminaries. So AD technology is just at high level, very high level, like adding sensors to the cars to make it drive right by itself. So if we put the sensors, for example, like here. So the goal of these sensors is essentially to sense the physical world, right? Like the road, the car, traffic horn, stop sign, so on and so forth. And then with this data from the sensor side, in the production AD systems, it usually has this modular designs. First goes through perception, then localization, prediction, planning, and control. And in perception, it usually first care about, okay, I want to be safe, right? I don't want to hit into some obstacles. So it will usually do object detection to detect obstacles in a single frame, and then do tracking, right? To track those obstacles across the frames. And this will be done for many different sensors. And in a sensor fusion process, it will try to make it more robust and then more accurate. And of course, there are many other domain-specific designs for lane detection, traffic light detection, traffic sign detection, and so on and so forth. So for localization side, some sensors like LiDAR can use, for example, point cloud matching to achieve global localization, and then combine with some traditional sensors, but in the more like ADV quality, much more expensive than the normal GPS and MU used in smartphone. Those go through a model sensor fusion process for higher accuracy and robustness, just like perception. So in this talk, when I talk about autonomy software, I mean the right part, right? This part doing this decision-making process, essentially. And then to attack this part, there are several attack vectors, and then one of the most so those most practical ones can be, for example, sensor attacks, right? For example, like if you tamper with the sensing input, you'll definitely change the input of the autonomy software and cause impact, right? So actually, for all these sensors, these 5 sensors I listed here, there are spoofing or jamming attacks being discovered like in prior work already. And also, you can jump like one layer ahead to attack the physical world, right? For example, by changing those road surface or the cars, and then this can indirectly, so of course, affect the autonomy software input, even if the sensor is perfect, right? So both are considered in my research because I think this is more practical in general at this point and at this particular point. So in this research space, and then so one of the famous prior work, if you want to to talk about the history of this line, is about traffic sign detection, right? This is something everyone knows now. So it becomes a very famous example by attacking the stop sign. So basically what they did is that they take the state-of-the-art camera DM model for object detection and then try to add some malicious stickers and posters on top of it. So this is some pictures I get from a CCS 19 work. So what they did is that they just add this colorful stickers, as you can see, which can make a stop sign appear or disappear, right? Which can cause problem, of course. So this kind of behavior is definitely very undesired, right? But still, missing a stop sign cannot directly make you crash, right? So so that's why when my group starts to work on this direction, so we first look at the obstacle avoidance the modules. So in particular, we look at the object detection, specifically LiDAR, because we think it's a very unique sensor for for autonomous driving. Which is published in CCS 19 and used in security last year. So what we did here is that we performed a first security analysis and defense design for 3D AD object detection. So the attack vector is LiDAR spoofing. So basically, this is kind of the design void. We actually replicated in the lab setting. Essentially, the idea is that you shoot some lasers to the LiDAR sensor to inject spoofed points. So that's the hell of idea. So by doing this, you can inject something like this, right? So several points in a scattered fashion and with a narrow angle. But the problem is that we soon realized that blind spoofing is not enough to cause end-to-end impact because for a real car that you want to inject, this is something like this, right? So it's like very dense and has a wider angle, so they look nothing similar to each other actually. And then we tried various angles and shapes of this injection, but it cannot actually spoof even one big obstacle as the model output at all. It just failed. So then we come up with the idea. So we know AI security, so we combine sensor attack with DNN like adversarial attacks. Basically, we couple this with the optimization process by first model this spoofing capability, and then use the global spatial transformation of the traces to find the optimal like the angle and then that transformation to fool the model itself, which is able to achieve a decent like 75% success rate, which is not bad. And in this particular case, if we map to the general challenges we talked about, so this is essentially mapping, we're filling the gap, a semantic gap of perturbations from the sensor spoofing a capability level, like the semantic level, to the component level input space, like DNN model input. And then also we use optimization with differentiability design and modeling to achieve attack effectiveness. That's another challenge I mentioned before. And next, we also care about whether this can cause some attack impact at the system level. So essentially, we do simulation and find out that this can spoof a fake front car at the perception output, which can cause emergency brake or denial of service. So by doing this, essentially, this is another challenge I mentioned before. This is the semantic gap of the component level of the errors, like the DNN model output misdetection, to the system level effects, like emergency brake or DOS. So this is obviously an interesting attack and with some insights, but I'm not going to focus a lot on this on this work specifically because that's a bigger problem. So later in the pipelines, I want to tackle. So basically, after this work, and there are also many other works trying to do something. Oh yeah. So that's a general takeaway I forgot to mention is that this basically so mapping back to kind of the general research value. So this one basically means that autonomy software level vulnerabilities can escalate the attack effect or damages at other layers, for example, sensor attacks. So interesting thought of combining sensor attack and a DNN attack. So essentially, so coming back to what I was talking about, so this work is interesting by itself, and also we found many other attacks trying to attack the in-road obstacle detection. For example, like by putting some stickers on the car, changing the texture, or just even paint the car in a like different looking, which has been shown can fool the camera-based DNN detection. And also, there's also another work trying to directly use projector to project into the road, which can let Tesla see ghost, right? Because for like image-based detection without depth information, so this one looks pretty realistic, like a person, right? But one thing we notice about all this work, including our own work, is that all of this are limited to attacks on a single source of AD perception. For example, like camera or LiDAR-based AD perception alone. But then if you look into this pipeline, there's something called multi-sensor fusion, right? So essentially, this is generally adopted by the production AD system like Waymo, GM, Pony.ai to achieve overall higher robustness and accuracy in particle less driving. You cannot just rely on one DNN model to drive in particle world at this point. And in this case, it's typically camera plus LiDAR, suppose that DNN based. And then in this case, assuming that not all perception sources are or can be attacked simultaneously is a big assumption, but let's put it there. So theoretically, that's always possible, right? To rely on the unattacked sources to detect or prevent a single source attack, right? Just in theory, if you think about it. So that's why, because of this, this is the basic security assumption is believed to hold in general. And then that's why there are many different papers trying to say, okay, for single source attack, one promising defense direction is to do multi-sensor fusion, right? It's widely recognized as the general defense strategy against existing attacks on AD perception. But then the problem is that if you look back, right? So all this belief that this can work is because of this basic security design assumption, which leads to a research question that we come here, that can such assumption actually be broken, especially in the practical AD settings. So in this case, this leads to our work, which just appeared just a few weeks ago at Oakland by studying multi-sensor fusion. So what we did is I want to perform the first study on the security of MSF-based AD perception. And then we want to be to directly challenge the security design assumption in this case. But if you want to explore the possibility that can we effectively and simultaneously attacking all the perception sources. For example, in this case, for the popular design is camera plus LiDAR. Can we do that? And then in this study, for the first time, it can allow concrete understanding about whether and how the use of MSF as a defense strategy can be fundamentally broken, right? If we are able to find such an attack vector. So we formulate this problem. So of course, for high practicality, we want to do physical world or sensor attack. And then we target a safety critical attack goal, like for example, like we want to fool the MSF-based AD perception in the victim to fail in detecting a foreign obstacle and just crash into it, right? So just very direct. So let's just make it fail to detect the obstacle. But first, right? So okay, to simultaneously attack LiDAR and camera. So how can we do that, right? So in this case, if we bring up the MSF design, so it's usually point cloud plus like the image, both DNN based, and then it is ideal if we can find a single physical world attack vector effective for both camera perception and LiDAR perception, because in this case you can save the deployment cost and then increase the practicality, deployability, so on and so forth. But the problem is that if we look at existing attack vectors, right? So if we put stickers or posters on the stop sign, okay, so in this case, it can affect for camera, of course, but it cannot affect LiDAR, right? Because it's just texture level changes. And also for LiDAR, so we know in my previous work, so we showed that, okay, shooting lasers can definitely affect the LiDAR point cloud, but then its effectiveness for camera is unknown. We don't know it yet. So in this case, we find a new attack vector, which is so-called this adversarial 3D object, something like this, like a mesh. So it's like 3D like object, we can manipulate the kind of shape and texture. So in this case, we find that this can be a physically realizable and also stealthy attack vector for MSF-based AD perception. And then we just place it in the roadway and then trick the victim to crash into it. And then in this case, we want to leverage shape manipulations to introduce adversarial input perturbations simultaneously to both camera and LiDAR. The key insight here is that because shape changes can definitely influence the point cloud, and also at the same time, because the shape is changed, it will also affect the image pixels, right? If you think about it, so simultaneously affect both. And then this is also easily realizable and deployable in the physical world via the advances of 3D printing technology. Actually, we did a bunch of this ourselves as well. And also it's stealthy, because this can be used to mimic some legitimate traffic object with like a worn or broken look, right? So okay, so now we find the attack vector. Here comes our design, right? So first of all, we start with a mesh, right? Let's say a traffic cone, and then we also have the road we want to target with a point cloud and images, and on the other side, so we have the MSF algorithm, right? So we want to like attack it. But the first challenge is about how can we combine them to synthesize inputs to the MSF algorithm, right? So this is mapping back to the general challenge, right? There's a semantic gap of perturbations from the semantic input space, in this case, the 3D mesh shape changes to the component level input space, right? In this case, the MSF algorithm input. So to address this, what we did is that we use the rendering. This is the first step. By, for example, for LiDAR, you can use recasting, and for camera, you can so like we can use there's some camera rendering techniques. There's some libraries there. Then we can solve this. And also, there's a step called preprocessing between the raw image to the MSF input in the production or industry-grade systems, which is necessary to improve the real-time algorithm performance. For example, like aggregating the features into like a lower dimensionality. And also like ROI, right? Like filter out this unrelated parts, right? So in this case, essentially, with this, we can then, what do we need for this process to be efficient and effective is to want to calculate gradients, right? So in the ideal case, we want to calculate a gradient to optimize the shape so that we can bypass the MSF. That's a high level idea in this framework. But then just like the previous challenge that I mentioned, so there's a problem of the effectiveness, right? Because here, if you want to use optimization-based solution, you want differentiable design and modeling. So how to make that to happen? So in this case, we have some solutions to customize some like rendering process for LiDAR and camera to make them differentiable. And also that's a unique thing, which is this aggregate cell level feature calculation for LiDAR. So this is very popular for state-of-the-art LiDAR object detection, because the raw LiDAR point cloud is just so big. So you need to aggregate them to calculate like into cell level, like 3D or 2D cell, and then calculate their average point height and intensity. So we design a novel like differentiable approximation design And basically, the key strategy is to use to estimate the discontinuous function using a probabilistic function based on interpolation. More details are in our paper, so I won't go into details in here. But I just remember this is the high level a strategy to resolve this. And this is able to have significant benefit to effectiveness. For example, we found that it can increase the attack success rate from lower than 10% to actually 100% in this case. So then with that, we also have some other designs to improve the smoothness and realizability, for example, by making the surface more smooth, and also improve the robustness by doing rotating and shifting, like EOT, something like that. So with that, let me show some demos. We evaluate on many different settings. So there's some demos which can be probably most direct. So in this particular case, as you can see, this is the setup we have. So we 3D print this traffic cone, and then on the right, this is the adversarial cone. As you can see, it looks like with some interesting noisy shape on top of it, and then on the right, it's just like a normal traffic cone. So let's see what will happen. So in this particular case, this is the benign case. And this is the leftist camera, right is LiDAR, and this is the benign one. So as you can see, it can detect this one in both, right? So because this is so obvious for human eyes that it's just red and big and have some shade on the LiDAR. So it looks obvious. But then if we change this to the adversarial case, I think the results would be totally different. So just using the same setup, as you can see, no matter how we move, and then in the normal ranges, it would just always evade both camera and LiDAR. And then also we have real vehicle in this case, trying to try it in a real vehicle setup. So on the right is benign, left is adversarial. So in this particular case, as you can see, we put the adversarial object in the middle of this road, and as you can see, the camera can detect the pedestrian pretty good. But in this case, it cannot be detected in both, just like the traffic cone case that I showed earlier. And also, we also do end-to-end. So this is because we cannot just let our car just crash into it. So we do like simulation. So we put the benign cone in the middle. So this is the Adversarial plus Apollo. And as you can see, it can just directly recognize it, stop in front of it. It's nice and safe. But then in the case of adversarial case, we just put the cone in exactly the same place, but then it cannot be detected in any of these frames, and then just crash into it, right? I guess the same case. So jumping back, yeah. So these are the demos, and then all the materials are on this the website. Just take a look. And then also we have many more evaluations. I guess the reviewers push us to do a lot more. In this case, we did it for robustness, smoothness, transferability, baseline comparison, so on and so forth a lot. There are papers for details. And also, last but not least, how about defense, right? So in this case, it's actually particularly challenging, actually from our internal discussions. So basically, if you think about traffic sign or road information, right, in general, you can fuse with map, right? If you have the map, you know, okay, I'm very close to the intersection, so I should be seeing some traffic sign, or not, or even the traffic sign is already in the HD map, right, in the high definition map. But then obstacles are actually dynamically placed, right? So anyone can just put a rock on the road, right? So in this case, you can only rely on the runtime information to do the detection. You cannot rely on map, prepare something that's not going to happen. So in this case, if you want to improve the runtime detection, you have to think about handling the DNN model, right, in this case. But then this is a challenging open problem by itself, because many existing methods like certified robustness cannot really apply here. So because this is a 3D semantic perturbation, and in many of these prior more robust methods like certified robustness only think about the 2D pixel level perturbations. It's just very big gap there. And also, for those, there do have some directly applicable defenses. For example, the input transformation, like the denoising or JPEG compression. And also, we tried a preliminary version of adversarial training, but this can at most reduce the attack success to around 66%, which is not quite enough to make it unexploitable in the real world. So the takeaway. So I just want to come back to the really high level messages from this research. So one thing is that the general design assumption that behind this, someone may think about this like a MSF as a defense can be fundamentally broken in some settings, in this case, in the particle settings. And then the second thing is that defense for this particular attack vector can be particularly challenging because it's like a dynamic road obstacle, it's just put in the road. Not part of the traffic transportation like infrastructure. So in this case, I think it calls for more future like defense into this, and we are in the process of open sourcing. So just check our website for updates. So yeah, this is about we did a lot on perception as you can see, but how about localization, right? So this is also interesting module that will directly take some sensor inputs. So particularly if you look at this module, if you want to study it, right? So just like perception. So if you do single source attack, so there's ultimately a question that can you actually bypass multi-sensor fusion? So in this case, I guess the natural question is that can actually this MSF-based localization be vulnerable in the same way, right? We don't know. But in this case, it's actually very hard, or particularly hard, because the main localization source for MSF is LiDAR and GPS. So like MU is mostly for data reckoning. So like it's basically like LiDAR and GPS. But then it's very difficult to attack both, right? Using like for example a single attack vector, because LiDAR is through lights, and then so GPS is through wireless like signals, right? So how can I do both? So then that makes it interesting, right? So maybe in this case it's more like more secure, right? More robust. So in this case it's also vulnerable, right? So we also did a first security analysis of the state-of-the-art MSF-based AD perception, AD localization, which got a Best Post Award at NSS 2019, and using security which has appeared in using security 2020. So in this case, we study specifically GPS spoofing, because this is so probably in the sensors, this is the most famous and long-lasting, still existing the problem in the real world today. And I guess my host and Sunil is a much better expert than me in this. So I guess just ask him about whether this is possible. But I guess in general, I feel actually GPS spoofing has been observed like a lot in the real world. So this is I guess a year-long investigation found that I guess nearly 10,000 spoofing events like global-wide. And then in this case, MSF is again generally believed to have potential to defend against the GPS spoofing. And there's a lot of people talking about this, just like the perception case. Because in this case, GPS cannot dictate the ultimate results. But again, come to the research question. So in the AD settings, whether state-of-the-art MSF algorithms are indeed sufficiently secure under GPS spoofing, right? So how about in this case? Can we just use single source attack to break it? So in this case, we are the first to define the security problem space for AD localization in this AD domain specifically. So for example, in this case, so we assume that attacker can tailgate the victim AD vehicle and perform GPS spoofing, which has been shown in some prior work on like GPS spoofing. And also, the goal is to aim to maximize the lateral deviation in the MSF output with no attack. For example, you deviate the MSF output to the right. So because of the control, so this will the car will try to correct its physical position to the left. So attack. So your MSF attack to the right, then the car will be deviating to the left in this case. So specifically, by doing this, you can just cause, for example, like going off-road. So these are all defined in a specific AD like space, like off-road attack or runway attack, specifically in this case. So we first do a security analysis because just like I said earlier, so in this case, we just use a single source attack, and MSF theoretically can defeat the single source attack, all right, in the ideal case. So we want to see whether it's really like vulnerable like, at all, right? So maybe it's just not vulnerable, so we don't waste our time, our time to build an attack on top of it. So in this case, we want to find the maximum possible deviation achievable by spoofing. So what we did is that we take a binary, which is this MSF. So this one is relatively representative because it's published in top tier, I guess, robotics like conference, and it has been tested with a fleet of like AV in many different scenarios, and the reported error is the smallest. So among the papers we survey. So we take this binary, and then we take data set from the real world sensor traces and synthetic like traces, particularly the synthetic one does not have any noises. And we split the trace to the attack windows and perform exhaustive search. We don't want to miss any attack opportunity. So in this case, we also define the success metric in this particular domain. So we look at those common lane widths and car width, and we know, okay, so these are attack goals for achieving off-road attack and runway attack on the local and highway. So these are just mapping that to concrete numbers for the benefit of analysis. So here's what we find out. So in the synthetic traces, actually, for all the cases, like 100% of the cases, the maximum deviation is less than 7.6 centimeters. So which means that it's far from which any attack goes. So you can just not even see like a shake of the car like from human eye. So this means that just by design or theoretically, MSF is actually not vulnerable to spoofing. I mean specifically for this MSF like binary. And then in the real world case, this is also generally the case. For the 76% of the case, it's less than even the smallest deviation we want to achieve in the attack goal. And then I guess the general takeaway we put here is that it can indeed generally improve the security against GPS spoofing. But then one interesting thing is that, again, we can still see around 13% of the attack windows can satisfy actually even the largest attack goal, like even nearly 3 meters. That's really interesting. So look at it, we see an interesting takeover effect, like an exponential growth trend of deviation somehow in its windows. And this is very different because we notice this because majority of the windows is just like a flat line, just nothing. But just like 13% of the windows can have this exponential growth, which is very interesting because of this exponential growth, it can actually get to like arbitrary attack goals if you want. So we find out that we did some simulation, find out that this is very similar to when the GPS is the only source. Like it can the spoofing can cause this exponential growth, and then in this case, actually the spoofed GPS inputs actually become the dominating source to an MSF, and later on, actually LiDAR becomes outlier, and they actually kick out the LiDAR signal. It becomes the only signal somehow, which can actually fundamentally defeat the design principle of MSF, like fusing different sources. This GPS becomes the dominating source actually in this case. So that's interesting. So we did a cost analysis, and we see that actually mainly this is appear in the time periods when the MSF states and the LiDAR localization outputs have some low confidence. So basically, they are not confident, so they generally take more updates from the GPS, which allows the GPS inputs to dominate the fusion process. That's I guess that's the logic about how this happens. And then this is generally caused by some dynamic and non-deterministic factors, like sensor noises, like algorithm inaccuracies. And then this is why this is actually not observed in a noise-free synthetic trace. But then what's interesting here is that even with the high-end AD sensors, those GPS, MU, and LiDAR super expensive actually, but these factors, these real-world factors are still very large and frequent that for GPS spoofing to practically exploit. So okay, so now I understand why. So the next is how to leverage this, right? Because this is very attractive because attacker, once they can cause this exponential growth, they can reach the arbitrary deviation goals, right? Because they already take over the fusion process. But then the problem is that it's very hard to predict or control because this is caused by non-deterministic factors. So I guess the only idea is to exploit in an optimistic way. So that's why we design a two-stage attack process. In this case, essentially, we have two stages. So first, we do some profiling, trying to like inject GPS spoofing and observe how the car behave. There's a minor less spoofing, and we want to see when the car becomes unstable, because at that time it is most affected by the GPS. And then once it reaches to a point that we say, okay, it's definitely more than it's normally deviating, it must be caused by spoofing, then we do a aggressive spoofing, try to exploit this vulnerable time window to quickly deviate the car. So we did some evaluation. Like still targeting MSF, this binary from Apollo, same success metric, and a data set decides Apollo trace versus highest. So here's what we find out. So the x-axis is the minimum attack duration, because in this case the attack is optimistic. So to capture this vulnerable window, you have to like tailgating for a longer time. So as you can see, the longer you spend or you want to devote to this attack process, the more likely you're able to capture a vulnerable window. And particularly when the minimum attack duration, like if you just tailgate for 2 minutes, you can achieve like 99% and also 96% like around that success rate for off-road and the runway attack. And then the whole attack process started from profiling to the to causing the toggle is around like only take around like 30 seconds to succeed. So and also because it's already taking over, so the achievable deviation is not limited to just the runway. So in this case, as you can see, the x-axis is the required attack deviation, and then you can see we can have like over 90% of chance to achieve even to 10-meter deviation in this case. So some demo. In this case, let me jump to here. So essentially, this is a simulation, and in this case, this is a car running Apollo, and this is a localization view. And as you can see here, the red dots are LiDAR, and then the blue dots are GPS. But in this case, you cannot see it. It's hidden by the LiDAR. And then the green dot, the green circle is the MSF results. So as you can see, this is before attack. It's generally very stable, aligned with the driving trace. And when the attack happens, this is the first stage. So we want to cause some larger deviations. So this is the case. We see the signal of like hitting the landline, and then we do aggressive spoofing. And as you can see, just getting deviated and hit to the barrier in this case. So specifically, what's interesting is on the left, as you can see, the blue dot. I'm not sure whether you can see that, but then it's deviating from the beginning because we are doing spoofing. But then the fusion results just quickly go along with the spoofing results, and then believe it. And even though the LiDAR result is actually correct, always correct, but then the fusion result is being checked in this case. And then we also have more, like all the materials are on the website again, and then we also have a lot more on evaluations, so including even a black box attack design, so which takes around half a day of profiling. See our paper for details. And then for defense, so essentially here, the fundamental solutions are not immediately deployable because, for example, you want to prevent spoofing, right? You need a new satellites and a new protocols. And or you want to improve the sensing and AD localization technology, but that's probably not going to happen. Yeah, we don't know when to happen. And then one practical way is to do detection, right? So this can definitely make the attack harder, but then this is not solved the problem yet. There are some prior work showing that all the existing techniques have known evasion methods, but I guess Niels definitely has more to say in this. But then in general, I think the GPS spoofing detection is still an arms race. So to best prevent this attack, I guess the autonomy software layer should always be prepared, right, for the spoofing to bypass the detection. So this definitely calls for autonomy software level design. So biggest like takeaway is that first of all, like so although theoretically secure, so as MSF as defense in this particular case can still be vulnerable to single source attack in practice due to some practical factors like such as noises and algorithm inaccuracies. And then for the sensor level attack, actually autonomy software level defense is still necessary because it can solve the problem at the root and also compensate the limitations of sensor level defense, right? So I guess coming back to the big research value like summaries at the beginning. So besides this theory work, we also have more work, for example, on the object tracking. So I won't go to more details. So this is the first to study object tracking. So we found that malicious stickers can be carefully designed to move a roadside object into the current lane, causing emergency brake, or move a front car away, causing a crash. And also we have a lane detection like attack. In this case, will appear in Security 2020. So like encourage you guys to take a look. So we look at a production lane detection DNN model, and we look at a malicious 30-row patch attack vector, which is interesting because on the road, in the real world driving, you many times see this 30 patterns. We found that this can cause the victim to drive out of the current lane within just 1 second. That's pretty quick. And then it also solves many of the general challenges like semantic gap from the 30-row pattern, which is the semantic input space, to the DNN model, right? The component input space. And also the semantic gap from the component errors, like the frame level lane banding to the GPS system level effects. For example, the end-to-end lateral direction, the lateral deviations due to the closed loop control, right? Because it has a feedback loop in CPS systems. And also effectiveness. So we also designed some differentiable modeling design to make more effective optimization to be possible. More can be seen in our website. We also look at the traffic light detection, but I probably won't go into too much details. This is also interesting design, like using GPS, because to improve the effectiveness and efficiency of the traffic light detection, industry-grade systems usually use ROI, like region of interest, but then the anchor is located using GPS. So if you are able to spoof the GPS, you're able to move for example, the correct traffic light out of the ROI causing a DOS, or move a wrong traffic light into the ROI causing red light running. So we have some interesting work in this as well. And then these are all design level security problems. So we also look at the implementation level problem, most specific bugs. For example, we have work at the XC 2020. In this case, it's the first comprehensive study of software bugs in the AD systems. So we also, for this problems we discover, we perform responsible disclosure, I guess as required in the security community. It triggered over 30 companies developing or testing AD vehicles to start vulnerability investigation, and some confirmed to work on fixes. So basically, this is the whole picture of what we did in the last 2 to 3 years, I guess. I guess I'm almost on time, so I will probably go very quick about the CV connected vehicle site. So this is also a very interesting space because they put communication devices to the cars called OBU, onboard unit, and also put device to the traffic infrastructure like RSU, roadside unit to let them talk. So there are some pilot deployments in the US already, like in New York City or Wyoming, Tampa. And then there are many autonomy software here as well. It can enhance software driving, like self-driving. It can enable smart traffic lights. It can also enable vehicle pollution tuning. And then there are some the security problems. So for example, in this case, it's more on the communication side. Like a malicious vehicle owner can control the OBU to send malicious data in this case. So like prior work find out that such spoofing attack can cause collision with significant traffic flow instability. And then to appear in this year's Usenix, I guess in the summer. So later in the summer, we are the first to design a automatic vulnerability discovery method, which using model checking to automatically discover 14 new design flaws that can cause DOS or decrease flow stability. And also, we are also the first to dig into the smart traffic light like security space. And in this case, we are the first to study the security of infrastructure-side CV systems called ASIC, specifically like intelligent traffic signal. And we CV data spoofing and find out that even one single tap vehicle can cause a massive traffic jam because of some new security vulnerabilities discovered at the traffic control algorithm level. There are some simulation demos there. You guys can take a look. And also, we do some defense on both the transportation infrastructure side and also the vehicle side. So just to summarize, essentially, my group is trying to actively developing research space on the autonomy software security in production AD and CV systems. So there's a website for this, just which has the collection of these efforts. You guys can take a look. So presently, I believe this is the beginning of this direction because all the importance and research value I talked about at the beginning. So now one thing is that we are mostly on the attack side, right? So as you can see, we're kind of breaking things like here and there. But then I think next, I will, so at least my group will be mainly focused on defense side. So really want to solve these problems in practice. And to build a community, like Niels introduced at the beginning, so I co-founded a workshop called AutoSec, which is co-located with NDSS. And then you guys can stay tuned for the next year's AutoSec. And then this year, also co-chair the Safe Things workshop with IEEE SMP, and more emphasis of the AD and smart transportation because of my background in CFP and PC recruiting. And then I guess you guys can take a look as well. And then in general, I'm always open to collaborations. And then here's my contact information. And then I will just end it there. And I guess I'm right on time. Niels.
Thanks a lot. That was very impressive work that you presented here and very interesting. So we do have some quick time for questions. Do we have questions in the audience with this kind of virtual format? I'm never too sure. If you have questions, please either ping me in chat or raise your hand in the participant list. I don't see questions, so let me ask a question. Hello? And I'll keep it short because yeah, we're kind of running out of time. But so yeah, all this work is very impressive. So I'm wondering for the big picture, long term, what you said you're in contact with the manufacturers, and my experience from talking to industry in different industrial control systems domain is that they are mostly not very convinced yet that these are going to be things that they need to put their money into in the immediate future. But clearly something should also be done. So what is your kind of your opinion on how could we try to, in general, get a good stable process to improve these things in general for everyone? Is there like, is there some kind of, I don't know, is there space for a spin-off here that does these kind of things like automatic testing for different manufacturers? Should there become some kind of standardization process? Should there be some standard data sets or something like this? What is your vision there?
Yeah, thanks a lot for the question. Yeah, that's actually, that's a pinpoint for my research as well. I think we contact those companies, some of them get back, but in general, you'll just end up like, nothing will happen, so nothing will improve. So they will generally say, okay, we are aware of this problem, and they had meetings with us, but then in the end, it just say, okay, so we'll improve, and then I guess never come back to this. So I think yeah, I think probably this will be a long-term process. I guess from the academia, the industry, that's always I guess a long-term process to make them like aware of this. So what I'm trying is that one thing is I want to build defense, because if you tell them that, okay, so I make your system broken, so they will be probably not too cooperative, but then if it's a defense, maybe they're more willing, right? It's like a software level update, so maybe you want to have it. So they are maybe more willing to talk. And then the second thing is that I guess on the attack side, so we want to be more practical. So a very common feedback I get from them is that they say, okay, it's in simulation, so not real. And then so even for the autonomous like driving cars, and they will have a car, but we don't have closed loop control because we don't want to hit it. So that's why we kind of manually drive it to collect data. Even for that, it's okay. So that's also not realistic. So I think just hopefully there are some test data or infrastructure efforts that can make this research more easier to show end-to-end impact. And then I think I'm trying to also want to do something at UCI, but and then I think in general, yeah, probably it's the best if we can have more real-world demonstration of it to raise their awareness. I guess that's but that'll be very hard for the academia people. So yeah, I guess but I guess that's a hope. So probably we can do something there.
Great. Maybe I'll contact you later, and maybe we should also have a chat offline. Okay, cool. Thanks a lot for this very exciting keynote. And I think we'll stop here with questions.